Talk about different forces that are exerted on an object. So we've heard about force being mass times acceleration. So if a box is or something is sitting on a flat surface, there is a force going straight down, which is going to be the mass times the acceleration. So the force is equal to mass times acceleration going downwards. Now, there's also another force called the normal force, which happens at perpendicular to the surface that they're sitting on. So in this case, it's going to go straight up. Now, if the object is sitting still, then those forces are going to be equal to each other. They're going to be in equilibrium. They're going to be balanced. So that's the normal force going straight up. So in a force diagram, we balance our forces. Now, there can be various other forces as well. There can be, for example, friction. So if the object is being pulled this way, towards the right in this diagram, then there's some friction at the point of contact down here in the opposite direction. We also may have some sort of, there may be some sort of resistance force, could be friction, could be air resistance, anything like that, some sort of force going in this direction. And then there may be another force going in this direction. It may be being pulled. Now, if these two forces, this one and this one, are equal, then the object's not going to move. But if this force is bigger than this one, the one on the right's bigger, the object's going to be moved towards the right. Now, sometimes you might get a force going on another angle altogether. So there might be a force, for example, going this way. Now, when that happens, in order to do the maths of balancing these forces, we do need to look at the horizontal and vertical components of that force. So we need to know what our angle is, and then we can find this horizontal component of that force and the vertical component of that force. Now, if we know this angle in here, then of course this will be whatever this is times sine of the angle, and this one will be whatever that is times the cosine of the angle. Sometimes you may get a different angle given, so you might get this angle, or there might be. So you can see here, if this is being pulled with a force of u in this direction with an angle of x, then this vertical component would be upwards with a magnitude of u times sine x, and the horizontal component, because it's being pulled towards the right, would be this direction towards the right with a magnitude of u cos x. In this diagram, we've got a box sitting on a slanted hill. Now, the box may be sliding down, it may be getting pulled up, it may be sitting still. The friction may be enough that the box doesn't slide, that it just stays still. Now let's consider some of the forces on this box. So we're always going to have that downwards force equal to the mass times the acceleration, and the acceleration in this case is going to be the gravity. We're going to have a normal reaction force, which is perpendicular to the blue line. So that's going to go in that direction. Now let's imagine the scenario where the box is being pulled up, and we're going to consider this to be a smooth surface. So we're going to forget about friction at this point. We're going to forget about any other forces. We're going to forget about, we'll just think about just these three forces. So there's the mass times the acceleration going down. There is the reaction force, or the normal force going that way. And then this one is some force being applied that's pulling the box up. So I'm just going to call it the pull. Now for this force, it's straight down. So that's pretty straightforward. That's just a vertical downwards force going down. For these two green ones, we do need to consider the horizontal and vertical components of those. So for this pull, we do have our horizontal component there, and our vertical component there. And let's say that the amount of force on that is U. So let's look at the horizontal and vertical components of that force. Now, the cool thing here is that this triangle here is similar to this triangle here. If you were to just pick this angle up and shift it up there, this line is parallel to this line, and this line is parallel to that line. So that angle right in there is x. So that's nice and simple to work out. So for that force, this will be u times sine x, and this horizontal component will be u times cos x. That's pretty easy to see straight away. Capital U, too late. That should be a capital U. Now, this one over here, the cool thing here is this angle is 90 degrees. So if I look at the horizontal and vertical components of the normal force, I've got my horizontal there and my vertical there. Let's say that the amount of force on this one is capital V. So the diagram's getting a little bit crowded. This angle here, that's 90. These three together, of course, are 180. So this angle is going to be 90 minus x, which also means, of course, that this angle up here is x. Now, I kind of like to just tip my whole piece of paper on the side in this situation, consider this one to be x, and look at this triangle here. So sine is opposite the x, and cos is adjacent to the x, of course, opposite and adjacent. So that means that this vertical component this time is the cos. So that's v cos x vertically going upwards. And the horizontal component this time, sorry, that should be a capital V. The horizontal component this time is v sine x, because our x is in a different position, it's up there. Now what we can do is we can look at all of those forces balanced. Now if the object is sitting on the surface, it's not being pulled away from the surface, then the vertical components may be in equilibrium. What we need to look at is what's in equilibrium and what's not. We need to balance our forces. If the object is not moving, then all the vertical and horizontal components will all be in equilibrium. They'll all be equal. The horizontals will be equal. So this u cos x would equal the v sine x. And this force times mass, force equals mass times acceleration going down, would be equal to the v cos x plus the u sine x. So let's have a look at this question from last year's HSC exam. A 50 kilogram box is initially at rest. The box is pulled along the ground with a force of 200 newtons at an angle of 30 degrees to the horizontal. The box experiences a resistive force of 0.3 times r newtons, where r is the normal force as shown in the diagram below. So let's just see how this diagram relates to that. So r is the normal force, so remember that's perpendicular to the surface where the objects touch. So that's going straight up in this case. It says it's 50 grams. And remember the force downwards would be mass times acceleration. So that's going to be the 50 multiplied by the gravity, because the gravity is the downwards acceleration. So there'd be 500 newtons going down. The angle is 30 degrees. So let's look at the components of this force where it's being pulled on an angle of 30 degrees. So what we've got here, in this direction, we're going to have 200 cos 30. And our vertical component, let's draw over here, that one's going to be 200 sine 30. Now, sine 30 is equal to half, so that just equals 100. Oops. This is root 3 on 2, so that's slightly harder for me to type on this screen. So 100 times the square root of 3 is our horizontal component. So in part 1, it says by resolving forces vertically, show that R is equal to 400. So if we consider our vertical forces, we do have this downwards force of 500 newtons. Remember, mass times acceleration, so 50 times the gravity. So we have the downwards force is 50 times 10, and that's going to be equal to upwards forces. So upwards, there is this R, but there's also this 100 going up from this pull in that direction. As I was looking at this, I was reading this as 50 grams. Now, 50 grams actually would not make sense at all. Because it's newtons, it needs to be kilograms, meters, and seconds. So we've got acceleration is meters per second squared, and it is 50 kilograms. So that G there relates to gravity. It's a little bit confusing because it does look like 50 grams. So in part 2, it says show that the net force horizontally is approximately 53.2 newtons. Now we know it's being pulled towards the right, so we know that this force going towards the right is going to be the bigger force compared to this one going left because it is moving right. So the net force would be to subtract those. So let's just say the force is equal to 100 times the square root of 3 minus 0.3 R. Now we know that R is 400, so let's just make that 400. And if you put that in your calculator, you do get 53.2 newtons. So that's how we answer part 2. The last part is to find the velocity of the box after the first 3 seconds. And I will do that with pen and paper. It's getting a bit crowded here. Okay, so in order to solve part 3, we need to consider our net force that we found in part 2. The force was 53.2 newtons going in the direction towards the right. So what we do know too is that force is mass times acceleration. So 50 times the acceleration is equal to 53.2, which means our acceleration is obviously 53.2 divided by 50, which equals 1.064. Now we're asked to find velocity, so of course we need to integrate it. Now I'm just going to show you 2 different things we can do here. So firstly, we know that that is dv dt is equal to 1.064. So v would be the integral of 1.064 with respect to time, which is 1.064 t plus c. We were told that initially it's at rest, so when t equals 0, v equals 0, so therefore c also equals 0. 0 equals 0, so plus 0. So v equals 1.064 t, and we were asked after 3 seconds, so when t equals 3, velocity is 1.064 times 3, and that is equal to 3.192 meters per second. Now there is a slightly different way we could have done that gets rid of the plus c basically, and that's to find the integral from 0 to 3. So it's like finding the area under the curve from 0 to 3 of 1.64 dt, and that will give us the same answer. So 1.064 t from 0 to 3, which is 1.064 times 3 minus 1.064 times 0, which is that same answer, 3.192 meters per second.